In this lesson, we're going to solve polynomial inequalities. A polynomial inequality is any inequality that can be written in the form of f of x is less than or greater than 0, or in the form of f of x is less than or equal to 0, or f of x is greater than or equal to 0, where f of x is a polynomial function. Below are examples of what we call polynomial functions. Now notice that not all of them are set greater than or less than equal to 0. In this case of the second one, you have some terms on either side. Actually, both the second and the third example has terms on both sides. So before you can even solve those, you're going to have to make sure that you get all of your terms on the left side and 0 on the right side. So when we get it in that form, that's a polynomial inequality that we can solve. And that's what we're going to be working on in this section. So here are the procedures for solving polynomial inequalities. So step one, you want to make sure that you, again, have the polynomial, express it as a polynomial inequality. In other words, the function on one side and 0 on the other. And the reason you do that is because of step two, and that is you're going to take the function and like you would do a regular equation, set it equal to 0 and solve for x, because those solutions where you solve for x, those are what we call the boundary points. And so what you're going to do is you're going to use those boundary points from step 2 to go to step 3 and make a number line where you label those boundary points, because it divides the number line into intervals. Once you get these intervals, you're then going to proceed to step 4 and test a point within each interval and see whether it produces a positive or negative. And based on what you're looking for, whether you're looking for only positive points or whether you're looking for only negative points, you'll then be able to locate that region. And once you locate that region, we're then going to not only graph that region, but we're going to write our solution set in interval notation form. And so that solution is basically that interval that satisfies the given inequality. So let's go ahead and get started with solving polynomial inequalities. So starting with the first one, it says solve and graph the solution set on a real number line. So step one, we want to get it in the correct form where we have all of our numbers on the left and 0 on the right. So we're going to have to move that 15 on the other side. And recall, to do that, you're going to have to do the very opposite. So the opposite of positive 15 would be negative 15. So let's go ahead and begin by subtracting 15 from each side. And so now that we have it in that form, we're going to go ahead and proceed by taking this trinomial and setting it equal to 0 so we can factor it and find our solutions, our x solutions there. So let's go ahead and set it equal to 0. I'm going to go ahead and factor the trinomial into two binomials. Now I'm not going to cover how to factor, because that's definitely something you should have learned already in intermediate algebra class. This is a pre-calc class, so you shouldn't be in this class if you don't know how to factor. Or some of you could be in college algebra class. But continuing on, once we factor it, you're going to take each factor there, set them equal to 0, and solve for x. So on that first one, when you get that as an equation, you're going to have to solve for x, you have to add 5 to each side And then, you know, of course, you'll have to divide by 2, and that's going to give you 5/2. Now, on the other one, we can just automatically clearly see that when we solve for that, that x is going to equal -3. So these are our two what we call boundary points, which we're going to draw a number line, and it is going to be at those points, these boundary points, that we're going to use to divide our number line into intervals. So I can already see that we're going to have 1, 2, 3 intervals from those boundary points. So let's go ahead and proceed to the next step. And the next step is to go ahead and make those intervals. So once we do our number line, we're going to see that we're going to have an interval that's from -infinity to -3. Then we have another interval from -3 to 5/2, and then the last interval there is from 5/2 to +infinity. Now we need to determine which of those intervals is our solution to our inequality. So let's take a look at the given inequality so we can determine our next step. Because our next step then is we're going to choose test points within each interval and evaluate for that number. So within this first interval that we have here, we can actually just choose the point -4 and plug it in. So what you're going to do when you evaluate a function, recall, you're going to simply plug that number in x's place to see what your output is. So again, our first interval is from -infinity to -3. We're going to use the test value of -4 and go ahead and evaluate it into our given function. Our given function, once we remove all of the x's and replace it with -4, go ahead and do the math. Once we do our math, and actually it really doesn't matter what the number is, you just want to know the output of that number, whether it is a negative or whether the output is a positive. And in this case, f of -4 equals 13, and it gave us a positive sign. So we can conclude that that interval from -infinity to -3, all the values within that region are positive in terms of their sign. Next, we want to take a look at the next interval, which is from -3 to 5/2. And within that interval, we can test 0 because 0 is one of the easiest points to plug in, because once it zeroes everything out, you can clearly see right away what you're left with. So when we plug in a 0 into the function and find f of 0, we can clearly see that our output is a negative number, -15. It's the only thing that's left. So that interval gave us a negative value. Everything within that middle interval there is negative in sign. So I'm just going to go ahead and write that there, so it's just to remind us that. Lastly, let's go ahead and test that last region from 5/2 to +infinity. And we can just go ahead and choose the point 3 if we like. So if we plug in 3 into our given function, remove the x's and replace it with a 3 and do the math, what we get out is a +6, so a positive value. And what you'll kind of notice when you do these inequalities and you're testing these intervals is you're going to kind of see most of the time, and again, that is not always, but most of the time, they will alternate. Like, for example, it started out with positive, and the next interval is a negative, and the next interval is positive. But you should go ahead and plug in test values and just don't assume that it is always going to be that way, because there are some exceptions where that it is not true. So always test a point just to be sure that you have the correct signs for each interval. All right, so we are done with step 4, and now that we have each interval done, let's take a look again at our given function, our given inequality, our polynomial inequality. So our polynomial inequality that we're given, once we got it in the form of to where it is, notice here, 0 on one side and all the other terms on the other, but all I need to do is look at this symbol. And this is a greater than symbol. So I'm looking for points that's greater than 0. So anything that's greater than 0 is definitely going to be a positive number. So I am looking for all regions that have a positive. So that means that that would of course be the two outer regions from negative infinity to 3, and then from, negative infinity to negative 3, and then 5/2 to positive infinity. Those are your positive regions, and that is the solution to this polynomial inequality. And then to write that in interval notation form, recall that infinities are always closed with a parentheses. Now, because you do not see a line underneath this symbol, that means it does not include the boundary points. So at those boundary points, we're going to have a parentheses there as well. And of course, a parentheses for positive infinity. So to write it, it's going to look like so. And that is how you write it in your solution in interval notation form. To graph it, this is what it looks like. So note that in some textbooks, some authors use open circles to indicate when it does not include the 2 points. And then some authors will use a parentheses to indicate that same thing. But either way is acceptable, whichever way you choose to graph it. And then below you see, again, that is the way you would write it in interval notation form. And there you have it, solving a polynomial inequality. Okay, let's do another example. Notice in this example as well, you have terms on both sides. So step 1, you need to make sure you get all your terms on the left, 0 on the right. So to do that, of course, we have to do what? That's correct. Add 6 to each side. So let's go ahead and do that. Now, it would make that a lot easier to factor if we can, if that first leading term there wasn't negative. So what we can do here, we can go ahead and either multiply or divide the whole thing by -1. When we do that, each sign there on the left, they're going to be their very opposite. So instead of the first term being negative, it's now going to be positive. The second term is going to be positive. And then the last term is going to turn into a negative, because as you can see, positive 6 divided by -1 is going to be -6. And then the other is a negative and a negative. That's why it produced a positive. And on the right side, anytime you have 0 on top, it equals 0. So now that we have the equation to where it's much easier to factor and solve for x, I'm going to go ahead and factor that trinomial. So it factors into two binomials. It's going to factor into x minus 1 times x plus 6. And we can do mental math to obviously see that our two solutions is going to be x equals 1 and x equals negative 6. So these are our boundary points, and it is going to be these points that are going to divide the number line into the different intervals. So at negative 6 and 1, that means we're going to have three different intervals, and that's from negative infinity to negative 6, another interval from negative 6 to 1, and then the last interval is going to be from 1 to positive infinity. So now our next step, step 4, we're going to choose a point within that region so that we can test that region, each region. So here we have our given polynomial is greater than 0. So that means what we're going to be looking for here is all the points that have a positive value, the regions where it's positive. So let's see, within each region, the first region we have from negative infinity to negative 6. Let's go ahead and use the test point negative 8. So into the given function, we're going to remove the x's and replace it with 0. Once we do that and do the math, we're going to see that we have an output of a positive number. So it really doesn't matter what the number is. What we're really looking for is whether the output is positive or negative. So in this case, it is a positive. So every point in that first region from negative infinity to 6 will have a positive value there. That's a positive region. So I know that that's going to be one part of our solutions because as we can see, we're looking for all values that are greater than 0, and a value that's greater than 0 is a positive value. Let's go ahead and test the middle region. It has 0. 0 is always your best point to check whenever you're in an interval that contains 0 because you can easily get your output value. So from negative 6 to 1, we're going to test 0. So let's find f of 0. We can clearly see the only thing left is negative 6. That's an output of a negative value. So everything within that region from negative 6 to 1 it will have is a negative there. So that is not going to be part. I can already see that's not going to be part of our solution. Next, we want to test the region from 1 to positive infinity, and let's use the value 2. So finding f of 2, once we plug that in and do the math, we're going to get an output value of an 8. That's a positive number, so everything in that region from 1 to positive infinity is a positive. And again, in our given equation, we were given that we're looking for values that are greater than 0, so that's all positive values. And again, here, as we can see, it is your outer regions. That is your solution. To write that solution, we're going to have parentheses on each end because you always close infinities with parentheses. As far as the boundary points, because this does not have a line underneath, we're also going to have parentheses at that point as well. And so that is how you write it in interval notation form. Now let's take a look at what the graph or the number line of graphing this polynomial would look like. And as you can see, this is how you would graph. Some authors will use open circles to indicate when it does not include those points, and some authors will use a parenthesis to indicate that as well. So either one is acceptable for graphing your inequalities. You do not need to do both. It is not necessary. You only do one or the other. I'm just showing you that you can write it in either way. And again, at the bottom shows you how to write this inequality in interval notation form. And there you have it, graphing a polynomial inequality. Okay, that's it for this lesson. Thank you for watching MVP Tutorials by your instructor, Dr. Speights. I hope you'll join me in the next lesson. Please feel free to like, share, and subscribe. Goodbye for now.